Welcome back. In this second part of the introduction lecture, we will see some basic terminology and notations that we will use throughout the course, and we will also review some simple notations of math that you will need later in the course. Let's start by getting familiar with some notations and terminology related to datasets. Let's take the following examples. On the left, we have a regression problem where we want to predict the price of some houses based on their size. And on the right, we have a classification problem where we want to predict the health state of a patient based on the uniformity of the cells and the age of the patient. The points that we see on these plots are called data points. A data point here refers to a house, and a data point here refers to a patient. These data points are also referred to usually as feature vectors or data examples or instances or observations. Here, the size of a house is a feature. And here, the age of the patient as well as the uniformity of cells are features. Features are also commonly referred to as attributes or variables. In our regression problem, the price is the output and can take any value. The output is also commonly referred to as the target variable because that's what we want to predict. In our classification problem, the health state is the output or target. It can take one of the three possible classes: malignant cancer, benign cancer, or healthy. Now suppose we have n houses denoted as x1, x2, x3 until xn. Each of those houses is characterized by three features: the size of the house, the number of rooms, and the location of the house, for example, the distance to the city center. So each house is a three-dimensional feature vector or a data point here. So it belongs to R3. When we refer to a data point or a feature vector, we represent it as a column vector, as in this case. We will use the notation xij, as in here, to refer to the jth feature of the ith house. So, for example, the first data point in our dataset, x1, it corresponds to the first house. And it has three feature values, so x11, x12, and x13. The second data point has also three feature values, x21, x22, x23, and so on. Now, when we talk about the full data set, we will represent it as a matrix of n rows and d columns, n houses and three features in this case. So we will have a matrix like this one. And we have n houses and d features, three features in this example. So the first data point, x1, is represented in this matrix as a line, as a row, right? The second data point is represented as the second row in this matrix. So yeah, our training data is now represented as a matrix. Now, the previous data does not contain any prices, but suppose that we want to train a supervised machine learning algorithm to predict the price of any given new house. To do that, we need to prepare a training data set. It consists of our input data x that we saw previously, and we also need the true prices corresponding to the houses that we have. These prices are given to teach or supervise the algorithm so that it learns to match or to model the relation between the input and the output. So in general, each house xi in our input data has a corresponding price yi. And therefore, our full training data set is represented by a matrix X and a vector of prices y. So for each house, each row in this matrix, we have a corresponding price. So here we have n houses, so we have n prices. Let's now talk a little bit about some notations related to the model. The machine learning model that we need to learn is actually a function that we denote by h, and this is usually referred to as the hypothesis function. So this model has a set of parameters, a parameters vector theta, and this vector theta is a vector of parameters, theta 0, theta 1, theta 2, and so on. And what we mean by learning or training is actually to find the optimal parameters on a given data set. So if you get some training data and you have some machine learning algorithm, training means that this algorithm will give you a model or will find the best parameters of the model on this training data set. Once you get this model, you can feed new data and it gives you the estimated or predicted output. For example, here we have houses characterized by just one feature, the size. So the input x is a one-dimensional vector or just a scalar value. H is our model. It's a linear model in this case. H of x refers to the predicted price. And this is the equation that defines our model. It involves the two parameters theta 0 and theta 1. By varying the values of theta 0 and theta 1, you get a different model or different line. In this example, learning means estimating the values of theta 0 and theta 1 that gives you the line that best fits this training data. We will see later how to estimate the best values of theta 0 and theta 1. As a quick reminder, theta 0 is the intercept. This is the value at which the line intersects with the y-axis. So for example, if you set theta 1 to 0 and theta 0 to 1.5, then you get a horizontal line, which is constant. If you set theta 0 to 0, then the line goes through the origin because theta 0 is 0, and theta 1 is the slope of this line. It's basically a over b, so 1 over 2 in this case, 0.5. If we set theta 0 to 1 and theta 1 to 1.5, we get a line which has a slope 0.5 and it has an intercept of 1. This is another example where we still want to predict the price of some houses based on the size of the house and also another additional feature, which is the number of rooms. So now we have two features. So our input data x belongs to R2. In this case, our linear model is a hyperplane as we have more than one feature. So we have three parameters now, theta 0, theta 1, and theta 2. And again, h of x is the predicted price for the house x using the model h, or using those parameter values. Now please pause the video and try to think about the following question. How would you write the equation of hx in a more compact format, for example using vectors? If you need more help, just know that you can use the dot product between two vectors. So if you have, for example, two vectors u and v, and they are of the same dimension, so they have the same number of elements, then the dot product of u and v is just a scalar value. This is not a vector, it's just a value. So the dot product is denoted this way, u transpose t. This is u transpose, it means we transpose this vector u to a row vector instead of column vector. And we multiply it by v. So it's basically u0 times v0 plus u1 times v1 plus u2 times v2, and so on. So how can you use something like this, a dot product, to answer this question? Please notice that you have something similar here and here. So please pause the video and think about it. Okay, so here is the answer. If we add 1 at the first coordinate of the vector x, so this is our x0, then our vectors x and theta will have the same number of elements, the same dimension. And if you compute the dot product between theta and x, so you have theta transpose x, then it gives you exactly this. So it's theta 0 times 1, this is theta 0, plus theta 1 x1 plus theta 2 x2. So instead of writing this equation, we can just write it in a more compact way this way, and we will use this notation a lot throughout the course. We mentioned earlier that learning or training means estimating the best parameters of our model. So what do we mean by the best parameters? It's actually the set of parameters or parameter values that minimize some cost function or error function. So we have something called cost function, and this computes how much the predicted output is different from the true output. So here we have our input data, x, and we have our true output corresponding to this data. For example, the true prices of our houses. And here we have our predicted output using our model or our current parameters. So this is basically h theta of x, the predicted output. So the cost function computes how much our predicted values are different from the true values. And finding the best parameters means finding the parameter values that minimizes this cost, or that minimizes this difference between the predictions and the true outputs. Let's see an example of a cost function. Suppose that you have a data set containing input data points together with their corresponding outputs, the true outputs. The cost of a given model on this data set is defined as follows. This is called the sum of squared errors. It is denoted by E, meaning error or cost. We have here the sum over all the training examples from 1 until n. This part here is the predicted output of the ith example. For example, the predicted price of the ith house. And this is the true output of the ith example. For example, the true price, the actual price of the ith house. So we have the difference between the predicted output and the true output. And this difference, since it can be negative, it is squared here. So this cost function or error function is called the sum of the squared errors. The cost function is sometimes referred to as the error function or the loss function. There exist different kinds of cost functions. Each of them have different set of properties. For example, someone might wonder why we didn't use the absolute value instead of this power 2 here. Well, you can, but this will be a different cost function with different properties. We will see later that it is usually easy to minimize this sum of squared error cost function, sum of squared errors, as it is a convex function. What this means is that there is a unique set of parameters that gives you the minimum possible cost. And it's therefore easy to find the best set of parameters, theta, that gives you the minimum cost. We will talk about this more in details later in the course. Okay, so here are some notations to remember. xi refers to a data point or a feature vector. So it's a d-dimensional vector, where d is the number of features. xij is the jth feature value of the ith data point in our training dataset. yi is the output corresponding to the ith data point in our training dataset. It belongs to R in regression, and it belongs to a fixed set of classes in classification. Capital X is the input data represented as a matrix of n rows and d columns, where n is the number of data points in our training data and d is the number of features. Theta is the parameters vector. Sometimes it's also, or those parameters are also called weights. So it's a p-dimensional vector. We have p parameters. H is our model or hypothesis function. H of x is the predicted output of the input x. E is our cost function. It depends on the parameters theta. So it's the cost of some model on a given dataset. Let's now review some simple basics of linear algebra. This is a matrix A, and this notation means that it has 4 rows and 2 columns. Aij refers to the value at the ith row and the jth column. A vector is simply an n by 1 matrix. For example, U has 4 rows, so it's 4 by 1. Ui refers to the ith item of the vector U. If you have two matrices A and B of the same dimension, for example, you have 3 rows and 2 columns, and here also 3 rows, 2 columns, then you can add them and get a matrix A plus B, which also has 3 rows and 2 columns. So you add them element-wise. 1 plus 4, it's 5. 0 plus 0.5 is 0.5, and so on. If you have a matrix A, you can also multiply it by a scalar value, for example, 3. And that gives you a matrix, 3 by A, of the same dimension as A, where each element of this matrix is multiplied by the scalar value. And of course, you can also combine several operations. You can multiply a matrix by a vector, or more generally a matrix by a matrix, since a vector is just a matrix with one column. So if you have a matrix A and another matrix B, then you can multiply those two matrices under the condition that the number of columns in the first matrix is equal to the number of rows in the second matrix. So in this example, we have 2 columns in the first matrix and 2 rows in the second matrix. So this multiplication is possible. And this gives you a matrix C, which has the same number of rows as the first matrix and the same number of columns as the second matrix. So here we have 1, 2, 3 rows, and here it's the same 1, 2, 3 rows. And here we have just 1 column, and it's the same thing here, 1 column. And to do this multiplication, you just compute the dot product between each line here with this column. So 1 times 1 plus 3 times 5. This row by this column. And this gives you 16. So the first row by the first column. First. And then the second row by the first column. Right? So 4 times 1 plus 0 times 5. And this gives you 4. And so on. Dot product between this and this. So 2 times 1 plus 1 times 5. And this gives you 7. The third row, first column. Third row, first column. Okay. So why are we talking about matrix multiplication? Suppose that our first matrix is X. This is our input data. It has n rows. This is, for example, the number of houses. And it has 3 columns. For example, 2 features, the size and the number of rooms, plus 1 additional feature, which is always equals to 1, as we discussed previously. And the second matrix is actually just our parameters vector theta. It is a 3 by 1 matrix because we have 3 parameters, theta 0, theta 1, and theta 2. And so the result, let us denote it by y hat, is also a matrix which has n rows and one column. So it's a vector of n values. And each of those values is actually the prediction corresponding to each of our houses. Why is that? Well, it's because when we are multiplying x by theta, we are actually multiplying each of those rows by this column, right? So this is basically x transpose theta, which is the same thing as theta transpose x. So we are computing the predicted price for this house x. If we take the second row here, the second house, and multiply it by this parameters vector, we get the predicted price for the second house, and so on. So basically, by just multiplying the input data x with our parameters vector theta, we get a vector which contains the predicted price or the predicted output for all our input data points. This is another example of a matrix by matrix multiplication, where the first matrix has 2 rows and 3 columns, and the second matrix has 3 rows and 2 columns. So this multiplication is possible because the number of columns in the first matrix is equal to the number of rows in the second matrix. And this will result in a matrix having 2 rows and 2 columns. So 2 rows and 2 columns. Okay, so let us denote this as a matrix A. This is the same thing, A. And what I want you to observe is that the first column in the resulting matrix, this one, is actually the multiplication of A with the first column here. And the second column in the resulting matrix, this one, is actually the multiplication of A with this column here, the second column. So why are we talking about this? Suppose that we have a matrix, this first matrix here, it's our input data x. And suppose that we have 3 different models. The parameters of the first model are those. So we stack them as a column here. So this first column corresponds to the parameters of the first model, the parameters vector of the first model. The parameters of the second model are those. So this column here is the parameters vector of the second model. And the parameters of the third model are those. So we stack them as a column here. This column corresponds to the parameters vector of the third model. So basically by multiplying x by this new matrix that we defined here, we get a matrix of n by 3, which contains the predictions corresponding to our input based on all 3 models. So basically the values that we get here, those n values, corresponds to the predictions based on the first model. And those values are the predictions, the predicted values based on the second model. And these are the predictions based on the third model. So just by multiplying x by this matrix here, we got a matrix containing the predictions of our houses based on 3 different models. Okay, a quick reminder about some matrix multiplication properties. First thing, so matrix multiplication is associative. So if you have A times B times C, this is exactly the same thing as this. However, matrix multiplication is not commutative. So if you have A times B, it's not the same thing as B times A. Maybe the only exception is if B equals to the identity matrix. In this case, it is commutative. If you have some square matrix where the number of rows is equals to the number of columns, and on the diagonal you have 1s and everywhere else the values are zeros. So this is called the identity matrix. If you multiply some matrix A by the identity matrix, you get the matrix A. And if you multiply some matrix by its inverse, you get the identity matrix. You also have something called transpose. So if you have a matrix A and you want to get the transpose of this matrix, you just transpose the columns as the lines as columns. So this line becomes a column here. This line becomes a column here. If you have a vector x of dimension d, then the norm of this vector is denoted this way, and it is computed as the square root of the sum of the squared values of this vector. For example, if this is our vector, then the 2 norm, or L2 norm, or also called the Euclidean norm of this vector, is computed as 3 squared plus 1 squared plus 5 squared, and all this under the square root. More generally, the p-norm of a vector is denoted this way. For example, the 2 norm is denoted like this, and it is computed based on this equation. So if p is equal to 2, then you get exactly this Euclidean norm. The Euclidean distance between two vectors x and z is actually the Euclidean norm of their difference. So you compute the difference between the two vectors x and z, and you compute the norm of this resultant vector, and that's the Euclidean distance between x and z. From the previous definition of a norm, we had the norm was equal to this. So if you have a vector u, its norm is this. But now let's talk about the norm squared. So let's remove this. The norm of the vector u squared is computed as this, but it can be written in a much more compact way based on the dot product between u and itself. So you have u transpose multiplied by u. For example, if u is equal to this, then the norm squared is equal to this. This is u transpose, and this is u. And this is simply 3 multiplied by 3, plus 2 multiplied by 2, plus 5 multiplied by 5. So this is exactly the same as this. Now, if you want to compute the squared distance between two vectors, so for example, we have a vector u and a vector v, and we want the squared Euclidean distance. So this can be written in a more compact way, for example, using u minus v transpose times u minus v. So basically this is the dot product between this vector difference and the same vector difference. Let's now talk a little bit about derivatives. Suppose that you have a function f, and this function takes some argument x. X here is just some argument, it's a variable. It's not a data point or feature vector as previously, but just some argument. And you want to compute the derivative of the function f with respect to x. So what does the derivative of x, the derivative of the function f at x means? Well, if this is our function f, then the derivative of the function at the point x is actually the slope of the tangent line. And the tangent is actually the line that touches this function only at this point. So the slope of this line is actually the derivative at this point. So if we take another point x, if we want to compute the derivative of the function at this point, then the tangent will be something like this. So it has a higher slope. So the derivative of the function at this point is larger. If you have some function that looks like this, and you want to compute the derivative of the function at this minimum point here, then the tangent would be something like this. The line that touches this function only at this point is this horizontal line, and it has a slope of 0. So the derivative of the function at this point is 0. So why we are talking about derivatives here? It's because imagine that this function is our cost function, right? And we want to minimize this cost. We want to find the parameters, theta, that actually minimizes this cost. So we know that the derivative of the function is 0 at the minimum. When the function reaches its minimum, the derivative of the function is 0. So we can find theta that minimizes this function by computing the derivative. We will see this in more details later in the course. You can find here a quick reminder about some rules for computing derivatives. For example, you have the sum rule, you have the power rule, you have the product rule, and you have the chain rule, as well as some other rules here. So please feel free to stop the video and revise a little bit those rules. You don't have to be familiar with computing derivatives in order to follow this course, because today you have some frameworks and libraries that compute derivatives automatically for you, but it can be useful to have a quick reminder about those. So once you do that, check this question, and here is the cost function that we introduced previously in this lecture. So if you want, you can try to compute the derivative of this cost function with respect to the parameters theta 0 and theta 1. And once you compute the derivative of this cost function with respect to theta 0 and theta 1, you can check that your solution corresponds to this solution that I'm given here.